It's time for the promised intro to physics calculus video. I know I said I'd have this last week. I'm sorry. Um, Things take longer than I think they will. That's usually how my life works. But we're gonna dig into it, do a little bit of calculus. This lesson applies it a little bit to physics actually. So we're actually gonna start doing some physics calculus here in this very first lesson. But mostly it's a math lesson just to give us the basic mathematical skills we need. And then the next physics calculus video, I promise there's going to be at least one more. I'm hoping for two more, make it a trilogy. But in the next physics video, we'll start applying what we learn here to some actual physics problems. Something I've always wanted to do is take the Thanos problem and make it a calculus problem. I don't think we're going to do that this year, but we can certainly look at gravity, because the big obvious error with the Thanos problem is that we treat gravity as a constant force. We calculate gravity and we keep it as the same gravity for the whole trip. But obviously, as the moon gets closer to the planet, it's going to feel a stronger force of gravity. There's that r squared distance value. So as r gets smaller, gravity gets bigger. And we have no way of accounting for that with algebra. So our physics Thanos project already has an obvious error, and one that can be solved by calculus, because calculus could actually track the force and the acceleration from the force as the moon gets closer and closer and gravity gets stronger and stronger. So again, don't think we're going to do that this year, but for those of you who aren't graduating, which is most of us, if you want to continue this conversation next year and actually do a better Thanos project with calculus, these few mini lessons will give us the ability to do that. So let's dive into it. First off, what do we already know from calculus from our little calculus mini lesson we did way back in the motion unit? So we already know that a derivative is a calculus term that tracks a mathematical function when a variable is constantly changing. So like, for example, in our physics gravity equation that we use for the Thanos problem, right? Gmm over r squared, r is constantly changing in this scenario. As the moon crashes into the planet, r is getting smaller and smaller. And so we need a way to track that gravitational force with r constantly changing. And that's what calculus can do for us. So a derivative could help us do that. And specifically, a time derivative is a derivative for time specifically, so where time is the variable that's changing. So the example I just mentioned is not a time derivative, that is a position derivative, where your position is constantly changing. So first off, we're going to focus on time derivatives. You can see three examples here at the bottom, our three graphs down at the bottom here. Those are three examples of time-based graphs, where time is a variable and x, v, and a are all changing with time. So to track that change, we would use a time derivative, where time is constantly changing, and we're looking at how do these three things, position, velocity, acceleration, how do they change with time? So we have Ron Burgundy up here. Our original function is position, our top graph, which is a red graph. And the derivative of position, which hopefully you remember from months ago, the derivative of position is velocity. So the first derivative of position is velocity, and velocity tracks how our position changes, right? How fast are you moving? How is your position changing? So we already knew that, but now we know the calculus term for it. And then finally, the green graph down at the bottom shows us acceleration, which is the second derivative. So the derivative of the derivative. So acceleration tells you how quickly your velocity is changing, which tells you how quickly your position is changing. So acceleration is two derivatives away from position. So we call that the second derivative. And you can take as many derivatives as you want. Some things like sine and cosine graphs, you can take infinite derivatives and it'll never go to zero. It'll keep changing in a pattern. It'll form a pattern. Other derivatives, like the ones we're going to do today, eventually will reach zero, where you've taken the derivative enough times such that the graph kind of flattens out and then becomes zero. And actually, you can see that here, jerk. So if we take the derivative of acceleration, you get jerk. And actually, the derivative of jerk is called snap, and the derivative of snap is crackle, and the derivative of crackle is pop. So snap, crackle, pop. So now you know 6 derivatives of position. But in this graph, you can see if you look down here at this graph below, you can see that the acceleration has 3 different values, so it does change, but each of those values are a nice flat line. So there's no slope to our acceleration, hence the derivative for our acceleration would be 0. So the jerk for this situation is 0. There would be no jerk because our acceleration isn't really changing, except at a couple points, and we'll get to that here in a few minutes. So what we call polynomials, which is what we're going to look at today, which is just your basic like x cubed plus x squared plus x kind of thing, with no sines or cosines or anything like that. Eventually, if you take enough derivatives, it will eventually go down to 0. A nice flat line at 0. And in this case, jerk is 0, because you can see the acceleration is all flat lines. So there is no jerk. Acceleration isn't changing. So let's take a look here. So on the graph, like we said, the derivative is simply the slope. And to estimate the slope, you can actually find the derivative, a good estimate of the derivative, by taking what's called a tangent line, which is a line that touches that graph just at one point. So you draw a tangent line and you use rise over run. You can actually estimate the slope of a graph that way and estimate the derivative. So I've drawn 5 tangent lines there now on our position graph, the red one, at 5 different spots. Now let's take a look at what the derivative would be at those spots. So let's start with starting point right here. Let's start with that starting point at time equals 0. At the starting point, you can see we've got a nice flat line there. That black line there is flat. So there's no slope, no velocity, so our velocity should start at 0. And indeed, it does. So that's checked off the list. So let's move to this next spot, this dotted line here. And let's look at what is our slope doing right here. And we don't have any exact numbers. We don't know what our exact slope is, but we do see it's pointed upwards. We have some sort of positive slope. And you can see that on our velocity graph, it's positive. Positive. So that checks off. So now let's look at that middle point right here. And you may recognize that from what we already know as a turnaround point. So what is the velocity at a turnaround point? Well, you can see from that flat tangent line there that has 0 slope, it is 0. In order for an object to turn around, it has to go through a point of 0 velocity, which is what our graph shows right there on the velocity graph. Then at our next points, let's look at our next 2 points. So here, we've got a downslope. We're going downhill, so that's a negative velocity, right? Going down into the negative direction. So our slope should be negative. And then here at the end, we've flattened out again. We've leveled off. We're not going anywhere. We've got a flat slope. So that means at the end, we should be going nowhere with a 0 velocity. And you can see those points right there on the graph. A negative velocity when we're going down, and then when we've reached the end, we come to a stop with a flat slope. We're not going anywhere. And you can see that here with a 0 velocity, right at 0. So I haven't taught you anything new yet. Sorry, I know we spent about 5 minutes there on review. And again, let's do the same thing to velocity now. So okay, we've got our velocity graph. Let's take a look at how that's changing, the derivative of velocity, which would be our acceleration. So acceleration tells us how quickly is our velocity changing, which is a derivative. So I've gone ahead and I've added some green lines, hopefully you can see that, some green tangent lines to our velocity graph there, so we can use those green tangent lines to get some estimates of acceleration. So I'm going to ignore the two in I'm going to ignore this one for right now because it's very weird. And we're going to ignore this one for right now. Those 2 points are actually impossible. You may remember me saying a couple months ago, sharp pointy things. Those are 2 sharp pointy things right there. The universe tends to work more like this with curves. Nothing in the universe can ever instantaneously change direction. That means it's going 2 directions at once, not really how things work. So you would never see a sharp pointy thing like the 2 I circled there. So because of that, mathematically, they do weird things. We're going to ignore those. Let's look at the other 3 points that are actually possible right now. At the very beginning of our graph, our velocity slope is sloping upwards. So our velocity itself is 0, but it's heading in a positive upwards direction. You can see that right here. That very first point, the velocity is trending upwards. It's got an upward slope. Same thing here in the middle. So hang on, I'm using red circles too much. Let's use a different color here. Let's go with purple circles. So that first spot, the velocity is trending upwards, and hence a positive acceleration. In this middle spot here, the velocity is trending downwards, right? That slope is going downwards. So negative slope means negative acceleration, which we have right here. And then finally at the end, it's trending back upwards again with a positive slope, positive acceleration. Okay, my circle. So what are we going to do about these sharp pointy things, right? This is more of a quick math lesson because physics works in the real world where the sharp pointy things don't really exist, where everything has a small, at least a slight curve to it. But here in Math Magic Land, we have these impossible sharp pointy things. And you can see that basically what happens, there's our 3 points, but basically what happens is you get these 2 spots where it simultaneously has 2 accelerations at once. Mathematically, that's what's going on here. We know that's impossible physically, but mathematically that's what's happening. So at these 2 spots, it has both this positive acceleration and this negative acceleration. Hence, it's impossible. We call things like that non-differentiable. It quite literally means you are not able to take the derivative. Non-differentiable points. When you have a sharp pointy thing, or an asymptote, or something like that, where the graph becomes physically impossible, we call those non-differentiable points in calculus. And we have 2 of those on this graph right here, where the acceleration is simultaneously 2 different values at once. That's physically impossible, so that doesn't really show up too often in physics unless we're doing something like this, which is theoretical and not real. But in math, that does show up quite a bit. Now you know what to do if you reach a sharp, pointy thing with 2 different slopes at the same time, and you can see that here. So if you look here at this point, coming into that point, we have a negative slope, and coming out of that point, we have a positive slope. So that point simultaneously has a negative and a positive slope. That's physically impossible. Mathematically, it is kind of possible, but we aren't able to take a derivative of it because you can't find the slope of something that has 2 different slopes. So we just say that's not differentiable, can't take the derivative, and it physically can't exist. Basically, what that means. So there will be times where not in the real world, but maybe in math, where you'll be given a graph that has some spots just like that, where you cannot take the derivative because there is no slope, or maybe there are multiple slopes, and hence you can't take that derivative. You can't find the slope of something if you can't find the slope of something. So basically, it for the background knowledge you need. Let's go do the math with a example problem that I've created with some Star Wars theme to it. Recognize the Sarlacc pit there from Return of the Jedi. Jabba the Hutt likes to use the Sarlacc pit as an execution chamber. It's some sort of living creature or something. I don't really know. Star Wars has some weird stuff in it. But basically it eats you, and that's his, execution chamber. So this poor young businessman has been loaded into Jabba's cannon here, and he's about to follow this pathway into the Sarlacc pit. He's going to get eaten. He starts 10 meters up off the ground. So basically your X initial or Y initial, let's start using Y for the Y direction here, now that we have 2 directions involved. So Y initial would be 10, starts off at 10 meters. And Jabba's really excited about this. So Jabba the Hutt is really enjoying his little execution chamber here. So we have, using our fancy physics technology, we were able to record his flight into the Sarlacc pit and get ourselves an equation. So we got that his height function of time. That's what h of t means there, ht. Right here is saying that we're measuring his height as a function of time. H of t is what that's called. And it's 10, which is our starting height, right? 10, plus 24.5t minus 4.9t squared. You may recognize that equation. It is equation number 1, right? X final equals x initial plus velocity initial times t plus 1/2 at squared. So I guess Tatooine has the same gravity as Earth, 9.8. So 1/2 of that is 4.9. And apparently the cannon gave him an initial velocity in the y direction of 24.5. So there's our equation we're working with. His height as a function of time in seconds, let's mention that we want our time in seconds, height in meters, is 10 plus 24.5 times time in seconds. So after 1 second, t would be 1. After 2 seconds, t would be 2, etc. And then we subtract out the gravity factor, which is 4.9 times t squared. So the gravity factor becomes more and more stronger every second, right? Because the velocity factor is just times t. The gravity factor is times t squared. So t is a little bit more important on the gravity factor. So I think I've introduced the problem enough. Let's get to the calculus of it here. So we're going to be learning something today called the power rule. It's a very, very powerful tool in calculus, and it's not too complicated. Really, it's just a subtraction and a multiplication is the only real math involved. Now, organizing and setting up everything correctly can be challenging. So I'm not sitting here saying it's easy, but the only actual math you have to do is multiply and subtract 1. So if you can subtract 1 and multiply, you can do the calculus. The trick is organizing everything correctly to make sure you multiply and subtract 1 from the correct numbers. That's the real trick. So when you have a polynomial like we have here, right, we have a t squared and a t to the first, right? Technically t here is t to the first. So we've got a t to the first there and a t to the 0, right? T to the 0, anything to the 0, I'll use t for an example, but remember, anything to the 0 equals 1. So t to the 0 equals 1. So right here, this 10 term, 10, is technically 10 times t to the 0. We just don't need to include the t to the 0 in there because it doesn't change anything. But technically, there's a t to the 0 term there. We've got 10 times 1, or 10 times t to the 0. So we've got a polynomial here, a second order polynomial is what we call that, because it goes all up to t squared, or t to the second. And so when you see a polynomial like this, you can take the derivative of it using the power rule, which is hard to explain. Like you'd hear me say multiply and subtract 1 about 8 times in there, and it's hard to explain verbally, so I'm just going to demonstrate it. Let's show it here, doing it in action. Oh, whoops, I covered up my little t to the 0 up there. Erase all that. Okay, so I'll give myself a little workspace here to work with. So our original equation is this, and we need to find the derivative of it. That's the goal here. That's what we're doing with all of this. I probably should have put that on there. I don't want to write a bunch with my mouse. But the goal is to find the derivative of this equation. Find, basically how is his height changing with time as we fall into the Sarlacc pit. So let's do the calculus. So first I want to show you how to write derivative. So if our function is h of t, and we're taking the time derivative here, we're taking the derivative of t, the time derivative. We're seeing how does something change in time. So t is our star variable here. T is the star of the show. So our derivative would look like this. dh, to show that h is the function we're changing, divided by dt. So dh dt is how you write the derivative of h with respect to t. That's literally what that means. So it means we're finding the derivative of h, and we're doing it with respect to time. So it's a fraction way of saying this dh dt fraction literally means we're calculating how height changes with time. So the top one is what you're calculating, the bottom one is what you're changing. It's almost like an independent and dependent variable, almost. Anyway, 10, let's start with 10. You can treat each term individually. So we're going to look at 10, then we're going to look at 24.5, then we're going to look at negative 4.9. Don't forget your negatives. So that's not 4.9, that's a negative 4.9. So 10, let's go backwards. Let's start with the negative 4.9 t squared, because the t to the 0 here, remember this is technically 10 times t to the 0, and that changes things. So let's start with the t squared term. So to use the power rule on a term such as this, negative 4.9 t squared. To take the derivative, first you take the exponent. In this case, it's squared, so the exponent is 2. Here, let's try to do this better. You take the exponent, and you move it in front of the variable, and you multiply. That was horrible. Can I get a better arrow drawing in this tiny little space? You move it, that'll work, in front. And you multiply by what's already there. And then, after you do that, you subtract 1 from the exponent. So let's see that in action. So we started with negative, gotta remember the negative. We started with negative 4.9 t squared, and then we do the power rule. So we move the exponent in front. So that becomes negative 4.9 times 2. We've got, again, negative 4.9 times 2, because we move that 2 in front of it, gives us negative 9.8. And then we take the squared, the 2 up here, so now we need to take care of the power. Now we need to take care of the power here. What do we do with the power? We subtract 1. So our power was originally 2, so we subtract 1. And we're left with t to the first, right? 2 minus 1 is just 1. So t to the 1, or t to the first. So negative 4.9 t squared, we took the derivative of it to make that negative 9.8 times t. We took the 2, we moved it in front of the t and multiplied by what was already there, and then we subtracted 1. So let's do that again for 24.5t. 24.5t, we remember, which is technically 24.5 times t to the first. Sorry, my mouse caught on something while I tried to draw that one. 24.5 times t to the first. So we take the exponent, which is 1, and we move it in front. So, and then multiply, right? So 24.5 times 1 is still 24.5, which is convenient, right? Multiply by 1 doesn't change anything. So we took the 1 up here, we took this 1 from t to the first, we moved it in front of the t, just like we did with the t squared, and multiplied by what was already there, which is 24.5. Now, just like last time, we need to take our exponent and subtract 1. So 1 minus 1 is 0, and t to the 0 is just 1. So let's actually draw that this time, right? 1 minus 1 is 0. So 24.5 times t to 0, which is just 1. So 24.5 times 1, which is 24.5. So when you have a t to the first, basically what happens is you ignore, it just goes away. If you have a t to the first, it just goes away, and you're left with the coefficient of what's left behind. That's what you do with a t to the first. Is same thing you do with a t to the second, except you have a 1 minus 1, which, equals 0. So now let's look at the 10. Sorry, before we move on, we turned negative 4.9t squared into negative 9.8t. We turned 24.5t to the first into 24.5. Now, what do we do with 10? So I'm gonna use this over here, but I need a little more workspace. So we have 10, which is the same thing as saying 10 times t to the 0, right? Because t to the 0 equals 1. So that's what we have over there, 10 times t to the 0. Well, our exponent is 0. So when we move our exponent out in front and multiply by it, we multiply it by 0, and the whole darn thing just goes away, right? Because you multiply by 0, so the whole thing goes away. So we don't have anything. This 10 just completely erases. When we take the derivative, any constant, any number that doesn't have the variable in it, so anything that doesn't have a t in it is going to just disappear when we take the time derivative. Same thing when you take the distance derivative and like do dh dx, anything that doesn't have an x in it in that case would disappear. It would go away entirely. So that's very helpful actually, right? Because sometimes you get whole giant nasty terms that don't have a t in it, so you just erase it. It goes away. The derivative doesn't care about that stuff because it doesn't have a t in it, so it doesn't change with time. The only things that have a derivative are things that change with time, meaning they have to have a time in the equation. So the only parts of this equation that actually change are the 24.5t, because there's a t in it, and that becomes just 24.5. The t goes away. And then this 4.9t squared has a t in it, so that's going to change with time as well. The 10 right here, our buddy 10, just goes away. It disappears entirely. It doesn't have a t in it, so it just vanishes and disappears. Our final answer then here is 24.5 minus 9.8t, right? Because t to the 0, so let me clean this up a little bit, right? 24.5 times t to the 0 is just 24.5, because t to the 0 is just 1, so 24.5 times 1. And we've got our negative 9.8t, which we recognize as gravity. That's how gravity changes the speed of things, is with that constant 9.8 acceleration, which you may have recognized. And this is still dh dt. And bam, we just turned equation 1 into equation 2 by taking the derivative. So you may recognize this equation as velocity equals initial velocity plus at. And in this case, acceleration is gravity, negative 9.8. So we've got our starting velocity minus acceleration times time equals our final velocity. So through calculus, we have turned equation 1 at the top, our position equation, into equation number 2, our velocity equation, by taking a derivative using the power rule. So that's the power rule in action. So again, recap, what is the power rule? The power rule is you take anything, so in this case it was t, you take anything with a t in it and subtract and move, first you take the exponent and you multiply it by, you move it down in front, so you multiply by the exponent, and then you subtract 1 from the exponent. So it's as simple as that. It's just very hard to explain. Hopefully this example problem answered some questions for you. So why does that matter, right? What sort of problem, what sort of real world problem might we actually answer through this process? So you might be thinking, okay, give me a calculus problem here, Mr. Simons. You showed me how to do the calculus. Why does that matter? So here's an example problem. Let's say we wanted to figure out how long does the man fly upwards before gravity starts pulling him down. So we want to figure out what is t, what does t equal at the turnaround point, right here. So if you look up at the picture now, please look up at the picture. We're trying to figure out how long does it take the person to get to this point right here. I just added an animation in there to make that happen. So that's what we want to figure out here. That's the goal. So let's use the derivative now to figure that out. So we were given this equation up here for its height, for the height. But we were asked a question about time and speed, and it wasn't directly about speed, but please remember, what kind of point do we have right here? What kind of point are we looking for? We're looking for a turnaround point. What is the velocity at a turnaround point? His velocity at a turnaround point is 0. So we know that his velocity at that point, his dh dt, right? Because dh dt is literally a slope. It's saying change in height over change in time, rise over run. So at this exact moment in time right here, his dh is 0. You can see that it's a flat line. It's an exactly flat line there, right here. So it's not changing with time at that instant. It's a flat line, so dh dt is 0. So we set dh dt equal to 0. His velocity is equal to 0 at a turnaround point. And 24.5 minus 9.8. So then we use algebra to solve for t, and we end up getting that 24. I'm sorry, it's not going to look neat because I'm still trying to write with my mouse here. So it's going to be a little sloppy, but you guys get the point. So 24.5 divided by 9.8 equals t. 24.5 divided by 9.8 equals 2.5. So 2.5 seconds. So the question was, how, we're given this equation for h. We're given the h equation right here. And the question was, using that equation, what is t when he reaches his maximum height? How long does it take him to reach his maximum height? This green dot up here on the line. So we had to use some calculus, right? We needed to figure out, okay, well, we know that's a turnaround point where his y direction velocity will equal 0. So we need to get an equation for his y direction velocity, and that's where the calculus came in. We used calculus to take the derivative of position to get velocity. Then once we had this velocity equation here, we could set that equal to 0 to calculate t. And yes, indeed, we've got 2.5 seconds. So that's where calculus can be very helpful for physics is, say we need an acceleration equation from this velocity equation. We take the derivative and boom, we've got acceleration. Say we need, just like we just did, we're given a position equation, but we need velocity. Take the derivative and you've got it. So the derivative it takes you from position to velocity. It takes you from velocity to acceleration, from acceleration to jerk, if that's what you need. It can help you take one equation that you use to solve for one thing and change it so you can solve for something else. Just like we did here, changing a position equation into a velocity equation by taking the derivative. So the last slide here is going to be some practice, so let's get to it. We just learned the power rule using a physics example problem. So now let's just practice the power rule here. No physics involved. Let's just practice our calculus skills, practice the power rule. So try taking the derivative of this equation first. I will be quiet for 30 seconds here. If you need more time than that, please pause the video and then resume the video once you have an answer, and we'll check ourselves. Answer's coming. Spoiler alert. Pause the video if you don't want to see the answer. Here it is. We've got that the derivative with respect to x. So that's a change from our practice problem, right? Last problem we did time, t. This is a position x-based derivative, but it works the exact same way. You still just move the exponent in front and subtract 1. And you can see that's exactly what we did. So let's use green for this first term here, x to the 4th. Man, my highlighter does not like to show up with this background color. Now I know, can't use this background color anymore, but that's okay. So let's use circles instead. Purple circle. Wow, that's not showing up either. All right, then black it is. We'll just do everything in black. X to the fourth. So what would we do with that term? We would move the 4 down to the front, then 4 minus 1 is 3. And that's what we have right here. We move the 4 to the front, and then x to the third is where we had an x to the fourth. Subtract 1, it's now x to the third. Our next term here was negative. And don't forget your minus signs. Negative 2.5x squared. Same thing, move the 2 down in front and multiply. So negative 2.5 times 2 is negative 5. You can see that here. And then what do we do with the squared? We subtract 1. So 2 minus 1 is 1. You can see that would be x to the first right there. So that is our, what we do with the negative 2.5x squared term is move the 2 in front and multiply, and then subtract 1. We're left with x to the first. And then this 42 does not have an x in it at all. So when you take the derivative with respect to x, it just goes away. So the 42 will just disappear because it doesn't have an x to keep it in the ball game, if you want to think of it that way. So your answer there should have been that the derivative with respect to x is 4 times x cubed minus 5x. This next one involves callbacks to some things from algebra class you might have forgotten, or that you might not have realized are actually powers. So this isn't a traditional polynomial. Usually polynomials have whole numbers for the exponents, and they're positive, like x to the first, x to the second, x to the third, like we've been doing. This is kind of a non-traditional polynomial, and there's two things going on here. We've got a fractional exponent right here. You don't see the fraction yet, but I promise you that's a fractional exponent. So a square root is actually to the 1/2 power. So that would be t to the 1/2 there. And then we've got a negative exponent right here, right? When our exponents are in the denominator, they become negative. So that would actually be negative 14 times t to the negative 2. So let's write that. Let's write that here. Our f of t, I'm just going to put f for now because I don't want to write more than I have to with this mouse, becomes t to the 1/2 minus 14 t negative 2. Negative exponents mean they're in the denominator. Fractional exponents means you have some sort of root. Like 1/2 is a square root. 1/3 would be a cube root. So on and so forth. So this is what f. This is another way of writing this. Those two equations are equal to each other. They're just written in different ways. So now that we have a nice, sort of polynomial here, we can do the power rule. So let's do the power rule, the power rule to take a derivative. So df over dt, let's take the derivative, equals, so one term at a time, remember. So we've got two terms here. We've got a t to the 1/2 term and a t to the negative 2 term. Let's start with the t to the 1/2. T to the 1/2, so we move the 1/2 out in front. So what 1/2? I'll use decimal form, 0.5. So that's same as always. You take the exponent and you move it to the front. So 0.5. And then we subtract 1. So 1/2 minus 1 is negative 1/2. And now let's look at the second term here, the negative 14t to the minus 2. So the first thing we want to do is take the exponent and move it down in front and multiply. So our exponent was negative 2. Okay, sorry about that. The bird has taken over my office, so I'm out on the couch, so the pen writing will look even worse now. But let's look at this negative 14 times t to the negative 2 term. We've got exponent is negative 2. You can see that here. Our exponent is negative 2. So first we want to move the exponent out in front and multiply. So negative 14 times negative 2 gives us a positive 28. And then subtract 1 from the exponent, which gives us, or negative 2 minus 1 is negative 3. So there's the derivative of that function, is 1/2 times t to the negative 1/2 plus 28t to the minus 3, or another way to write that would be 1/2, right? 0.5 is 1/2. And then when you have a negative exponent, you can put it in the denominator. So t to the negative 1/2 is actually 1 divided by t to the 1/2, which is the square root of t. And then plus 28 divided by t cubed. So t to the negative third is the same thing as saying divided by t cubed. So this and this are the exact same thing. They're just written in two different and perfectly acceptable mathematical forms. So your teacher at some point may have told you that having fractional exponents and negative exponents are not okay. Or they may have told you that having a square root in the denominator is not okay, or something silly like that. That's just math teachers being particular. Mathematicians are kind of silly that way. In physics, no, I can't imagine you'll ever have a physics teacher tell you that either of these ways is wrong. They're both exactly the same mathematically. They're just, personal preference. Would you rather have everything as exponents, or would you rather have things as fractions? But they're the exact same equations. So again, what did we do? Let's take a step back and look at how did we do this. First, we had to turn these things that aren't exponents into exponents, because we need exponents to do the power rule. You can't do square root minus 1. That doesn't make sense. But you can do 1/2 minus 1. So we turn our square roots into fractions, fractional exponents. And then also do not forget that our denominator exponents are negative as well. So when you take this divided by t squared here and you move it to the front, that's t to the negative 2. Negative. So those are just a couple tricks. So long story short, what did we just learn here? We learned that we learned that we can take square roots and turn them into fractional exponents, which can then be power ruled. We also learned that we can take our exponents in the denominator, such as t squared in this case, and turn them into negative exponents. So we turned this into that. We turned this into that. And now we can do the power rule. And the power rule is still the same. You take the exponent and move it in front and multiply, and then you subtract 1 from the exponent. That's all we did here to take the derivative. Is for both of those pieces, we move the exponent out in front, so we move the 1/2 out in front, and then we subtracted 1 from 1/2. And same thing for the second one. We moved the negative 2 out in front, and then we subtracted 1 to get to negative 3. So a little complicated. Really, the only way to get good at this is through practice. So let's practice. So test yourself with these three. So the first one here, test yourself with these three. So the first one is just a basic polynomial. We've got a t cubed, a t squared, a t to the first, and a t to the 0. Remember that plus 2 is technically plus 2 t to the 0. Then we've got that middle one there that has a negative exponent and a fractional exponent. So you'll want to. And I don't know if let me. I'll come back to this one here in a second. So if you're like, wait, t to the 3/4, what the heck do I do with that? I'll show you here in a second. Or x to the 3/4, and then you've got that last one there, which is pretty challenging. That last one, if you feel good about that last one, then you've got the power rule down. Hopefully everyone's able to do the first one. That one's pretty straightforward. The second and third one can be tricky, so give them a try and challenge yourself. But x to the 3/4 is equal to the 4th root of x cubed. So the denominator is the root. So we've got the 4th root here. And then the numerator is the power. So x to the 3/4 is the same thing as the 4th root of x cubed. So that, again, and that's true with most calculus. The most challenging thing about the calculus is the algebra, right? All of these x to the 3/4 and things like that. The calculus is you multiply and subtract 1. So the calculus math is actually pretty straightforward. It's setting it up that's the challenge, which is all algebra. So the hardest thing about calculus is algebra. Same thing as last time. Answers will appear in 30 seconds. So pause the video until you've had a chance to give these 3 practice problems a shot, and then you can resume the video to see the answers. Great. That was about 30 seconds. So if you don't want to see the answers yet, make sure you pause now. There's that first one. So check yourself and ask me if you have any questions. Just send me a chat. There's that second one, a little more challenging, or you may have written it this way. Again, it depends on if you like fractions or exponents better, but either way of writing those are mathematically correct. And then that third one, the really, really challenging one. So there you go. So that's the power rule. Again, long story short, I've said that about 8 times, and it's gotten to be a pretty long story. I apologize, but you guys asked for this. You wanted the calculus. I spent a long time putting this together, probably 4 or 5 hours in total. So I hope you guys like it. But what we learned today is how to take a derivative of a polynomial. And for each part of the polynomial, you take the exponent and move it in front and multiply, and then you subtract 1 from the exponent. That's all there is to it. Now, that doesn't always work, right? If you have something in your equation that's not a polynomial, like I said, sine or cosine or logarithms, natural logarithms, anything like that has different patterns of taking the derivative. So this pattern, the power rule, works for polynomials. When you have a, t or x to the something, to the t squared, t to the 1/2, or something like that, that's where you use the power rule. So yeah, that's it. Please send me a chat if you have any questions. I will certainly find some way. I think I'll make an exit ticket for this video, just like I do for our mandatory assignments, but this one will be worth a couple bonus points. So if you sat through this for a whole class period and you learned some calculus, then fill out the exit ticket on Teams, get a couple bonus points, and when I get a chance, the next lesson will be about something called an integral, which is actually the exact opposite of a derivative. So if you have velocity and you take the integral, you'll get position. So integrals go backwards. So it's like the anti-slope is one way to think of it. So we'll look at the integrals in calculus video part 2. But that's all for this one.